we propose a hierarchical object representation for spatial robot perception. Our representation starts from raw RGB-D perception, including image-based object segmentation and depth-projected point clouds. It then progresses to dense object mesh reconstruction, compact superquadric representation, and finally inflated superquadrics. Together, these layers form a multi-purpose object representation for autonomous robot applications. Given an input RGB-D sequence, our framework builds the scene through 4 hierarchical layers. First, Layer 1 segments objects in each frame and selects the best view for each object based on semantic feature variance. After that, Layer 2 then uses the selected views and masks to generate object meshes and estimate their poses, forming an object-level scene reconstruction. Next, Layer 3 abstracts the reconstructed meshes into compact superquadric representations, reducing the scene complexity while preserving the main object geometry. Finally, Layer 4 inflates the fitted superquadrics to conservatively cover the original object geometry, producing a lightweight and safe object-level representation. With this hierarchical representation, we demonstrate 3 downstream applications. First, for high-fidelity reconstruction, the RGB-D sequence is processed by our reconstruction module. Based on the best view selection in Layer 1, each object mesh is generated from an informative observation and assembled into a complete object-level scene for visualization and simulation. Second, for map alignment, we use the superquadric representation from Layer 3. Given 2 reconstructed scenes with camera trajectories in their own local frames, we first find object associations across the 2 maps. Besides comparing object semantic features and centroid locations, we also compare their superquadric parameters to capture geometric similarity. This allows us to estimate the relative transformation between the 2 maps and align them into a consistent global frame. We evaluate this alignment method on an indoor simulated dataset, where the results show accurate alignment of local odometry maps within the same scene. We also demonstrate its robustness in real-world scenes, where disturbances such as illumination changes and camera pose uncertainty may exist. Finally, for robot navigation, we use the inflated superquadric representation from Layer 4. Since superquadrics are defined by implicit functions, we can efficiently determine whether a 3D point lies inside or outside an object surface. This provides an efficient way to perform collision checking and occupancy map construction. For example, given a reconstructed scene, if objects are represented only by bounding boxes, the planner may fail to find a valid path between the start and goal positions. In contrast, our inflated superquadrics provide a compact but more accurate approximation of object geometry. This enables the robot to identify feasible free space and successfully plan a path to the destination.